Today we're going to be talking about project ideas, sort of get some resources out for you, and hopefully, you also start thinking about the projects. And then the main part of the class is going to be doing some sort of functional programming with Lean, showing how monadic stuff works, do notation stuff, and then some tactic writing. And so we'll see how this goes. Yeah, so last time we looked at.
Where do we find these new tactics?
What was that?
Because in the, I think that there is some old documentation that they don't tell out this new tactic. It's like info and
Yeah. I mean, the documentation sources have varying levels of detail about it. In any case, sorry about the restarted computer there. And so let's get back into it. So, right, so let's talk about project ideas. So, I collected a bunch of sources here of things in Mathib, things not in Mathib, things that people say that they want in Mathib. So library overview. So this is just a collection of things that are available in Mathib. So this gives you some sense of sort of how far along in various areas Mathib is. So like what kinds of things occur in category theory or different kinds of numbers, complex numbers or p-adic integers and so on. If there's an area that you don't see listed here, then it's possible that that might be a good idea to investigate. There's also this list of undergraduate mathematics that is in, this is based on some French curriculum on undergraduate mathematics, so this is just all the things that are listed as entries in the curriculum, and then there's also a list of sort of the complement of that, so all of the things that are on the curriculum that do not occur in Mathib, so all of these are possible things that we can do. And then there is this old page on undergrad low-hanging fruits, so beware that fruits may have already been plucked. But these are hopefully accessible. As for tactic writing, this issue here is a list of tactic. So the origination of this list is this was a tactic porting issue. So the idea was that there was a bunch of tactics that existed in Lean 3, and then they all had to be rewritten for Lean 4. And this was tracking the status of them. The port of Mathib was completed, but it was completed without actually finishing this list, which means that there's still a bunch of tactics that Mathib just didn't use enough to make it worth port, or they just either managed to work around it or it wasn't used all that much to begin with. And because of that, some of these tactics didn't actually get ported. So you can see there's a key here. So the ones that have check marks have been done. The ones that have little diamonds here are unclaimed. And I expect that they're all unclaimed, or all of the claims here are long out of date, because this is an issue from 2022. But this is basically a list of tactic ideas, essentially, for things that once existed in Lean 3 and no longer exist in Lean 4, and getting it back in Lean 4 would be, it's clearly a thing that people would appreciate. So, yeah, looking at some of these tactics, they come with, I believe they come with some descriptions. So this is the Mathlib 3 documentation for R cases that has an R cases question mark tactic, for instance. This no longer exists in Lean 4, and it would be lovely to get this back. This does case splits on so you give it a term, but you don't say how to case split, and then it just looks at it and sees, it's a product of ors of whatever, and it suggests a pattern, right? So it says like, okay, I'll try, do angle brackets if it's a pair, and do ors if it's an or, and so on. So that might be like an accessible thing to do, and that currently doesn't exist, right? Etc.
For studying, it's a good list of tactics we should know.
Oh yeah, well, this is a list of tactics which don't exist. So
Okay.
these are the names that they used to have. There is a list of tactics, somewhat under construction. You can actually, let me show you a tactic called help. So the help tactic will list all things of a certain kind. Here the kind is tactic. So here's showing me all of the tactics, and it does so by checking like Lean's database of like what would parse in tactic position. So this is actually a complete list. At least this is a complete list modulo the imports that you have. So you have to import everything if you want to see everything. And in fact, let me import mathlib.tactic just so that you can see all the mathlib tactics as well. Shouldn't be too weird. Yeah. Right. So here you can see, adaptation node, check, Lean search. We talked about that one. I think they're sorted by in alphabetical order, basically. AC, Refl, ASOP. ASOP is a good one to know. I think I mentioned that one a little bit. Any goals, apply, etc. So there's a huge list here of all of the different tactics that people have worked on. So if you're interested in just, the canonical complete reference to all tactics that exist, there's a way to get it. Okay. The 1,000 theorems list is an extension of the previous 100 theorems list to have, more theorems. So this is sort of like a benchmark for theorem provers of a kind. The idea is that we should have this list of famous theorems from Wikipedia, basically, and currently 164 of them have been proved in Lean. And then there's also a list of all, if you just take the complement, then you get this list, which is all of the things that, these are all references to Wikipedia articles. I think it would be nice if they were linked, but you can just look them up. And so, yeah, these Fermat it's a weekend project, you'll be fine. You can get 5 of these done.
In the Wikipedia they explain how to prove it.
Well, they'll explain what the theorem is.
Let's not explain.
Sorry, what was the help tactic again?
What was the what now?
The help tactic.
hash up.
Okay.
And you can also do like help attr to look at all the attributes, or help term, I think. Yeah. Help term shows all of the term constructors, like array brackets and or and all of those things. And I think there's also one to tell you what can't exist. Yeah, what categories. Like if you don't even know what are all of the words that I'm using, like tactic, a term, or whatever, there's actually quite a few more. Okay, so you can pick one of these, look it up, and this will tell you about what it is, and you might end up with a theorem in economics, in which case maybe it may or may not be so suitable for formalization, because this list of theorems is not particularly curated for areas. So those are all things, and then also there's this method active project list. These are active projects. These are being worked on currently, but a lot of them are quite large projects, and so it's possible that you can find within one of these projects like some piece of it which you think you can get involved in, like solid abelian groups or étale spaces, or all these things. So on Tuesday, that is to say the next class, we will not have a class. Instead, we will have meetings, and I'll have 10 minutes, I think, to have meetings with you. So figure out, if you're going to have a pair project, figure out who you're going to pair, and then DM me sometime between now and Tuesday, and then I'll assign you a slot, right? And so we will, we'll basically talk about what your ideas are for project, what your area is. I can try to suggest a project if you're not having any ideas, and hopefully that should help with setting you on the right track for being able to get a project. Okay, any questions about all this? And of course, if you are just here to audit and you don't want to do a project, then that's fine, you don't need to come. All right. Okay, so let's do programming. So we've already seen earlier that we can do examples like this. You can define a function, like x plus y, and then you can evaluate it and get a result. So that's already basically programming, right? But if you want to do something more imperative, we use monads for being able to sort of organize these calculations. So for instance, here I'm using this io.print function to print hello world. And when I run it, I get hello world printed. And I mean, at this level, it doesn't look too much different from just returning the string hello world. But I think I can try it with just a string. And I think it will look slightly different. Yeah, it puts quotes. This one doesn't have quotes. Big difference. I think what actually happens is that when compiling these functions, what it will actually do is compile to print of whatever it is that you gave it. So that's where the actual printing happens. Okay, so just a quick recap on monads. I'm not intending to make a monad tutorial here. I'm hoping that you all know basically what they are, but a monad in general has two operations called pure and bind here. Sometimes this pure is called return, but we're going to call it pure. So the idea is a monad is a type constructor, like IO here, and it has a function which, given alpha, returns an IO of alpha, called pure, and then given a IO of alpha, we can sort of unpack it and use it in another computation that returns IO. So we can use this alpha in this function f that takes an alpha and returns an IO beta, and then the whole thing produces an IO beta. So this is composition within this monad, and that function is called bind. So for instance, there's a function IORAND that returns a natural number in the monad, and so we can use bind on that. We get a random number A, use it on rand 0 to 100 to get a larger random number B, and then return the pair. And so we have constructed a IO returning a pair of nets. And so when we run it, you see we get two random numbers. They look pretty random. And you'll see every time I type anything, the numbers change because it's rerunning this action. So every time you get different numbers. So that's something that you wouldn't be able to do with a pure function like this foo example. There's a syntax for this bind, rather than having to write it in the style where you write a bind operator and fun whatever, which by the way, there's also the Haskell style notation using this funny fish looking symbol like that. So that also works. But the usual notation we'll be using is you write do and then let with a back arrow. And the back arrow is saying, let's use a bind here, get this value, and then the continuation is this function here, right? So these two functions are doing the same thing. Return is kind of similar to pure, but it's not the same thing. In Haskell, pure and return are just aliases for each other, but here return is more like an early return. It can actually do interesting control flow. I'll show an example of that in a bit. There's also this neat syntax here where instead of having to do these lets, you can actually just write a back arrow before an action, and this thing desugars to this. So like this expression, it sort of looks through the expression looking for these back arrow operations, and then it pulls them up. Okay. You can also do for loops. So here we have this for the syntax of it is more like an iterator style for loop. So you can give it some kind of iterable collection. In this case, it's a range from 0 to array.size, and you get indexes I. We access an array. So I guess maybe I should mention briefly here. Array is basically list, but it has a different structure in the runtime. It's like an array in place rather than a linked list, which is how one represents a list in most functional programming languages. This is just an actual array. So here we're looping through the numbers from 0 to array.size, and we're accessing the array at that index I. If it's equal to this value A that we're passed in, then we return I, and this is an early return, so we exit the for loop right here. And if we don't find anything, then we return none. You might notice that I don't write return here. I actually can't. The reason is because option is a monad, and return takes in an element of sort of the content of the monad. So like here, if we replace this IO with option, pure is really the sum function already. So when we write return here, it's expecting me to return a natural number. So if I want to return none, I actually just sort of use it directly as a monadic action here. Okay. And so the purpose of this function is essentially it's going to walk through the array. The first time it finds an element which is equal to my input, it returns the index of that value. So this is just finding like the first index of an element. And you can see that it actually gets desugared quite a bit by this do notation. So a lot of this stuff is just simulated.
How do you simulate the early return?
Yeah, good question. So the for loop complicates matters. I might actually simplify this just for display purposes, let's just say let I equals 0, so that we only go through the loop once. So what do? So the early return appears, so this if statement here turns into this if here. So then it just does pure I, else it does the rest of the block. So in particular, if I had something else, I don't know. Oh yeah, I think that would work. Yeah, so you can see that the let x equals 1 ended up here inside a local variable called doJP, and then that gets called only in the else block. So this is a way of, this JP stands for join point. It talks about like continuations of the program, and they get assigned to variables, and then they're called in certain circumstances. So this is a way of ensuring that this rest of the computation doesn't happen if you hit this return. But this is all, so do is a really complicated macro. I'll be talking about macros in a bit.
Do you mind just re-going over what pure means in the lean context? Like I know it from applicatives.
Yeah, so it's the same. So
Okay.
pure is the pure from applicatives, and also the return from monads
Okay.
in Haskell. Return is the one that's different, but pure is just that function.
Okay.
Okay. Right. And it gets more complicated when you're in a for loop, because for loops are done using combinators. So here we have this function for in that takes sort of the body of the loop and produces a monadic thing for the entire loop. But then it needs to be able to store the fact that it was sort of requested to return from the outer block. And so that's what happens here with this for in step done, and then there's some pattern matching in order to ensure that like all of the control flow works out. So it's a pretty complicated desugaring, but this is all just syntactic manipulation of this for loop syntax.
Yeah, because early returns usually are exceptions thrown and caught by the caller, right?
Right. So this is not, this is a source level transformation of code. This is not actually implemented using exceptions or things like that, which don't exist in it. Well, there's a monad except if you want to do that semantically, but here it sort of simulates it syntactically.
Yeah, it's kind of an exception because you use some and
Yeah. Option. So option and accept allow you to, in the monad itself, perform exception-like behaviors. The encoding here is actually not doing that. It's explicitly like keeping track of all of the branches of computation and so on in order to construct something that's just using the monad operations. I'll show you some more examples where this gets even more interesting. Right, so this for loop here gets desugared to some, well, not exactly this, but something equivalent to this. So this is sort of how you can do all of that without using any monad stuff. You're just using function calls. And I want to stress that like this isn't some magical, like this is not extra stuff that's in lean. This is really just sugar for calling functions that call functions and so on. Okay.
then you have the yield. What is yield?
Oh yeah, so for in, if you look at the type of for in, it return in the body part of this for, so here you pass it, I think this is the collection, you pass the initial value of some kind of state that you're going to be threading through the loop, and then you pass this function which is like the body of your loop, and the function returns a for in step. What's a for in step? This is like either continue the loop or stop the loop now. it has, yeah, I can just show you. So for in step of alpha has a done and a yield, and it this alpha is the state that we were going around the loop with. So we either say done in order to say we want to early exit the loop now, or we say yield in order to say we want to continue the loop to the next iteration. So when you go through the loop and nothing interesting happens, then you return yield of whatever the current value of the state is. And if you have an early exit or a break or anything like that, then you use done. And that's how this return gets encoded. So this return is supposed to say, get out of this for loop, and so then we just say done, and then it returns some I, and then here we bind on it in order to turn it from an option, because here I'm actually returning an option of an option, and I need to turn it into just one level of option. And the yield is saying, keep going around. Okay. Another cool thing that you can do inside do notation is mutable variables. So mutable variables don't normally exist in Lean, but they do exist inside do blocks, and it simulates them. So we can actually look at, actually let me show you just a basic example. So I can do something like this, where I mutate the variable sum. And if you look at what happens, well, it just gets turned into let binders, right? So I said let mute sum, but he just says let. And here, this mutation just got turned into another let. So this is a kind of mutation that you can do even inside just using shadowing, right? But mutation is a little bit different from that, because you can also do conditional mutations, and you want the mutation to stick around. So what happens then? In that case, it has to sort of thread through the state of like, what was the final value? So in this case, this do.jp, which is the stuff after the if statement, is being passed the new value of sum in one case of the if, and the old value of sum, that is to say this initial value, in the other case. And so that's how it encodes this kind of stuff. So there's a bunch of just random stuff that the do compiler is doing behind the scenes in order to make it act as though you have proper mutation inside the thing. But for the most part, you can just use this and it works just fine. The other thing that I was showing here is you can do mutation inside a loop, and that's where it makes use of that state that was in the for in. So the for in had this state variable, which here is r. So we just say r is the initial value of sum, and then change it in the loop. And so that's how mutation is also distributed. But in any case, you can just write this code, and then it looks like, you know, C code running, and one can be happy. You can also, so here's a variation on this. Here I was using this array brackets I bang operation, and what this says is if the array is out of bounds, then it panics, which is a very low-level exception that you don't usually want to get in a regular program. But because we have dependent types here, we can have a proof that our I is in bounds and use it. It doesn't even look like we're using it, but we are in fact using it. And this syntax it attempts to prove that I is in bounds using all the stuff in the current context. And if it fails, it gives you this error message suggesting maybe put a bang or something. But here, if we have this h that says that I is in the range 0 to array.size, we can prove that our array is in bounds. And so that's like a win for dependent types, I suppose. And again, we're summing the array. Here, actually, it's not really necessary to do this stuff with indexing. We can actually just pass the array itself into this for loop, and it just loops over the elements of the array, and its return value is the values inside the array. And of course, if we don't like do notation at all, we can do it Haskell style, right? And just use fold out, because that also works.
There is this dot notation as well. But,
Okay, fine. Let's actually do it Haskell style. There you go. All right, so maybe you've gotten tired of evaluating things through eval and you want to actually produce a program at the end of the day. What you can do is you define a function called main, you put some stuff in it, and then you modify your lake file to add this lean.exe. You can also say when you create a project that you want it to have an executable in it, and then it will create this main, it will create a template for basically this kind of thing. But in the end, what you end up with is the ability to do something like this. So I can run Lake, and Lake is how you build these projects. I mean, I've usually been just building them inside the editor, but you can also use this to, oh yeah, and that's why I didn't have Mathlib Tactic, is because otherwise all of Mathlib gets linked into my executable, which is unnecessary.
So we have yield, remember in Python that you have a yield that you generate a iterator.
This does not have yield expressions, no. That would be a lovely addition to me. That would be possible. But quite complicated. I guess I still linked in a bit too much. But okay. There we go. So you should usually compile less into your program if you want it to be a regular program. But what we did was we compiled this into an executable, and the executable should now be available somewhere here. There, we have our lec5 executable, and we can run that, I think, just like this. Yes. And now you can see the results. This here is this println bang is a macro which does interpolation. So these are just expressions, so here we're running foo22, which is 4. We're running bar, which is hello world. I actually don't know why it prints. That's interesting. Where there? I don't know why it's there.
They don't have a syntax highlighting for this print line.
They used to, actually. I think that the highlighting must have changed. But there is normally highlighting here, actually. It could also be that I'm not actually using any variables. Does this? No. Yeah, no, I don't know.
What is the exclamation mark in the print?
I guess it's supposed to mean like macro. I'm not sure that has held up as a convention, but like originally this was borrowed from Rust, where that's the convention. Well, it's not even a convention; it's part of the syntax. But there are quite a few macros that don't do that. So I'm not sure how debug trace doesn't have this, but it has a similar syntax. But yeah, so println is println, but as a macro. Println without it is, at least in the IO, this is just, like you can see this, this is just a literal string. But you can also make it into, there's a version which just gives
now
me
there
the
is,
tree
it's highlighting. But...
No, it's highlighting the braces, it's not highlighting so, yeah, a bit of inconsistency here. But yeah. And that's how you get a program and run it. I also want to mention some thing to be aware of regarding how mutation works on data structures that aren't like natively functional. So array, as I mentioned before, is like a literal array of values. Now, if you know anything about functional programming languages, you'll know that they quite often don't have a data type which is just an array of values because it's difficult to update those values without making a copy of the entire array, right? So instead they'll do some tricks with finger trees or some other interesting tree-style data structures that allow you to act like arrays. But Lean doesn't do that. It gives you an actual array. And now you wonder like, oh, how's that gonna work? Here's an example where we're gonna construct an array of all of the natural numbers from 0 up to some bound. The way we do that is we construct an array of zeros, we pass it to this go function, and the go function loops over. I've written this sort of explicitly using calls just so that the do notation doesn't get confusing here, but we're just doing a loop over I, and we pass the current value of array, and then in each iteration we set one value of the array to its own index. So at the end of this we'll end up with an array where all the values are the numbers in order, and so then when we call sum array, we add up all of the numbers, right? So this is the number that we would expect from doing so. This is like n times n minus 1 over 2. And you can see that it's doing this quite fast. When we get to, we're getting just under a second for 1,000,000 numbers. Here's another version of the function, and you might have to look carefully at this in order to notice the difference between the two functions. The difference is that the go function takes 2 arrays as an argument and it just ignores the second one, right? And what I do is I pass the new value of the array in each iteration of the loop to go. And then I pass the old value of the array also to go. This makes a huge difference. You'll see that like this completes in like 200 milliseconds, and this one I think completes in something like 10 seconds, 15 seconds. A long time. 15 seconds, okay? So very, very major difference between these two functions. The only difference between them is that here I passed an argument that's not used at all, right? The reason why this makes a difference is that at this point, when the set is called, Lean sees that their array has to be held around so that it can also be passed to the function later. So this forces this set to actually be a copy of the entire array. Whereas in this set, this is the last occurrence of array. And because of that, it sort of owns this array, and it can destructively update it in order to pass to the next value. No one is going to see the fact that we've modified it because this was the last use. It actually does this check sort of dynamically, like it just runs the code, and if when you're running it you see that the reference count on this value is 1, then you know that it is safe to update. But as you can see, it makes a big difference in practice.
Is there a way to enforce the linearity so you don't accidentally get copying?
That is a PhD thesis. People haven't tried, let's just say. As it currently exists, no, there is no mechanism for being able to do that. But it is definitely something that people would like to see. Okay. I'll comment that out. That doesn't slow down other things. So let's get to actual tactic writing. So this is the easiest kind of tactic writing. I declare a macro called easy. It's a grammar class. This is not exactly a type. This is like the parser version of type. So we say what grammar class it lives in, and then here we give it a quotation where we also have to say the grammar class that we're producing, and then we give an expression in that class. So here it's trivial. So we're saying the trivial tactic as a piece of syntax is what you should return when running easy the tactic. So when I write example true by easy, it sort of unfolds this thing into by trivial, and so this proves it, right? So that's what it takes in order to define a tactic. Easy. Here's a more complicated tactic where we have arguments. So here I want a version of simp where I take a list of terms that I'm going to pass to simp, but then I'm also going to add in one extra thing of my own. So the syntax is, well, I can give in addition, so here I need to give sort of how my tactic gets parsed. So I say my simp, and then open bracket, and then a list of terms separated by commas, and then a close bracket, and I bind it to tm. And then here we sort of do the inverse. We need to construct syntax, and I say it's a tactic, and the tactic is simp bracket, and then I just insert nat.addLeftCom and a comma, and then this is like an interpolation where I have a comma separated list of things. Those things are tm, which is a term. The result of this is that I can now run my simp with a list of terms, and it will insert nat.addLeftCom, and so this will be the same as though I wrote this. And that's exactly what this macro is expanding to, and as a result, I can prove this. If I leave this off, then I think it won't work. Okay. And so syntaxes take this expression here, and also this expression here, well, ish, are following this grammar of syntax declaration. So you can write like foo in quotes, that just means the literal token foo. If you name something like term or some other named parser, that refers to whatever is produced by that parser. The star means 0 or more, the plus means 1 or more. If there's a comma before it, then it means you're separating by commas. And then you might sometimes also see this comma question mark, which means, you know, you can have an optional comma at the end. Here, when you have two in a row, so for instance, here we have a string literal, and then we have a term sequence separated by commas. That's a sequence of parsers. This is not application. This is very confusing because everywhere else in Lean, this means application, but here, when you have just adjacency like this, that means like one parser, then the next. And then also this or symbol means to parse B or Q. There are also two ways to write a syntax declaration. So you can either have, like what I did here, that is to say syntax, and then the name of the new parser, colon equals, and then a parser declaration. So here I'm going to declare a closed class as either foo bang or bar bang or baz question mark, right? The other way I can define it as an open class is I declare syntax cat with open class, and that gives me a new syntax category called open class, and then I can declare multiple things whose sort of type is that open class. So here I say foo1 and foo2 are open class. And now I'll demonstrate, like, okay, so let's have a tactic that takes an open class and then a comma and then a closed class. So here I can use foo1 for my open class and foo2, or I can use foo bang or baz question mark. Those work. So at that point they sort of look the same. The difference though is that my open class, I can keep adding things to it after the point at which I declared it. So here I declare it on this declare syntax cat line, and then I start adding things to it. And anything that's been added to it so far can be used. But like once I add another thing to my open class, now I can use foo3 as well. I couldn't do this foo3 before, of course. So this isn't declared, but once I have declared it, then it's fine. And whereas my closed class is fixed for all time, it only refers to these three things exactly. Okay. And you don't have to just declare tactics. You can do terms as well. So here I'll declare boo as a term, which it takes. This is like literal syntax boo, and then you add one of these closed classes. So I have boo foo and boo bar. So the way that you make use of these closed class terms is that you can just pattern match on them, and then you say the class that you want it to be. So basically, there's a quotation inside a match, right? And you don't have to handle all of the cases, and actually, even if you do handle all of the cases, it won't be exhaustive. You always have to have a fallback pattern where you basically, this is the usual thing people do, is just say throw unsupported. And so this works on foo and bar, but when you try to use it on baz, it says that the function hasn't been implemented. And this suggests that you could actually implement another elaboration function for this, and that is the case that like this isn't necessarily the full declaration of the thing. You could add a second declaration that handles anything that's unsupported by the first declaration, for instance. But in general, that's sort of what you can do. And so all of these, and I guess this is also showing that like the typing is not the same as like with a regular. This is not just a regular function, right? Here, boo foo is returning hello world, whereas boo bar is returning 4, right? They actually have different types, so you can't really type this as a function. Okay. Elaborators do more than just expand to other code that already exists as like this is like a lean expression that expands to another lean expression. Here we can have one that just runs code. So here we're going to define a tactic test mean that's going to like solve the goal. So here's the way that this works. So the first line, we're going to get the main goal. And then we're going to get the type. So a goal is a meta variable. A meta variable is like a hole in a term. And that hole has a type. So that's what you would normally see in a. So here we have the type of the goal that we are sort of expecting. So if I get the main goal, that'll be a meta variable, which is something of type true. I can check whether that type is defiq to the constant true. If it's not, then I'm going to throw an error that says I only proved true. And then if it is, then I'll assign true.intro to it and then replace the goals with empty because I closed the goal. And so you'll see that this is a very basic implementation of the trivial tactic. This checks if the goal is true, and if so, it closes. And we can see that this, if run on false, it says I only prove true things. So that's a good thing. But it only works literally on true. It only actually proves the true thing. And then here is also a basic definition of the exact tactic. So you can write the exact tactic just by doing something like this. Again, we get the main goal. We elaborate. So here I've taken a term as an argument to my tactic. I elaborate that term. That this is a piece of syntax. This is like a lean expert. So that's what the elaboration does. And we pass it the type because this helps it figure out how to interpret that piece of syntax. Like there are some pieces of syntax that require the expected type, and so we should pass along that expected type whenever we have it. We don't have to though, we could put none in here. This is actually an option. So we could do that and that would also work. But it would give less good inference. And so we get an expression, we assign it to the goal, and then we get rid of the goal. And so that is my exact. And let's do some more examples using it. So if we have h, has type nuts, and we want something with type nuts, then I can pass an H, and that works. Here's an example where things can go wrong. So these tactics don't have a whole lot of guardrails in terms of what they generate. So they are allowed to generate bad things. So let's say that I have a tactic like this that just believes that everything is trivial. So it's going to take the goal, assigns it to trivial, and then moves on with its life. And so when we apply it to true, everything works, right? Because it is indeed true. We can also prove something like id of true using the same method, because trivial has type true, and true is definitionally equal to id of true, so that's fine. But if we try to prove something else, like false, using our everything is trivial, we get an error message, but it's a different kind of error message. This is a very low-level error message. You can tell because it says kernel at the beginning. Basically what's happened, and this will not happen at a very useful position. It's not highlighting everything is trivial at all. It's actually highlighting the entire example, because the term that was constructed is malformed, but it doesn't notice until it does a double check at the very end of execution of all the tactics of the declaration. So it basically generated a term, and then the kernel, and then the entire term was given to the kernel, which sort of rechecks the term using just the core axiom, the rules of the type theory itself, and at that point it realizes, hey, you tried to put in trivial as your proof, but the goal is false, so that's not okay. So that's what happens. My assumption is an example of, here we have, we're using the context this time, so we need to actually look at so get LCTX, this is get local context. This is looking at the list of assumptions sort of in our goal. So that's this AX, X dagger, and H. And so I'm going to make a version of assumption which only does assumption on variables whose names start with H. So we're going to get the type of the goal. We're going to get the local context. We're going to loop over the local context. Check if its name starts with H. If so, then we're going to check also that the type of the thing matches our goal. And if so, we assign the goal, we replace the goal with empty, and then we return because we're done. And if we go through the whole loop and we didn't find any, then we say that no assumption matches. So this one works. It finds that this H here is solving the goal, but this one doesn't work. It says no assumption matches. Okay, so I think it's probably time to take a break, and we'll come back in 15 minutes.
Is there a REPL for lean, or
Is there a repr?
REPL like
REPL.
lean interact, or like GHCI for lean?
So that's kind of the VS Code mode. Yeah, I mean,
Like
you can write just eval in a lean file, and it will, act as a REPL for you if you want. There is actually a project called REPL, but it is for machine learning people, and it does JSON input output, and it's for Python. It's much closer to a REPL for the purposes of doing some kind of training activity or something like that. It's not actually like GHCI.
Or you could have a Jupyter plugin. The Jupyter. It's also a lot of work.
I don't remember exactly what I did to get the problem, but I tried to make a I have since replaced the code, but I tried to make like a type alias, and then I had issues with like, oh no, this is not a valid expression of that type because it did not expand the type alias. Is there like a standard solution to that kind of issue?
I mean, you can unfold type aliases.
Can I like?
Well,
But if I want to do it like in a type declaration, so if I have an index type or something, and so I my issue is that I couldn't write uh, the proposition itself, like and I can't use tactics and stuff in the type string.
I mean, you can. You can actually write types if you want. I might have to see code.
Yeah, I'll see if I can reproduce it.
So a question about these, so you have this very fancy do, which does lots of nice assuring, but once you try to verify a program written with do, I guess you have to deal with the desugar version there.
Yes, and it is somewhat nightmarish sometimes.
So it's a kind of trade-off, like you save doing all this, oh, I have to define another recursive function just to do this loop, and then it's hard to prove stuff about it.
It is frequently easier to refactor a definition to not use do notation in order to make it easier to prove properties about it. Like using tail recursive functions is a common technique. It compiles to the same kind of thing, and it's easier to reason about than all of these do JPs and whatever. Like there's a bunch of mess that you end up with. A lot of it is sort of redundant too. Like you get pures that go nowhere and stuff like this. So yeah, if you're trying to get like a nice looking term, probably this is not helping. There are plans for Lean to get a nicer, like the ability to do proofs, some kind of like add invariants into loops, or like get something that looks more like Daphne, where you can like just insert assertions in places and then maybe have an SMT solver solve it, or maybe have Lean, tactics solve all of the obligations that pop up.
Right.
And then that way you can do your proof like on the spot, instead of like having to post hoc reason about this desugared thing.
Yeah. I have a question about the unifier. So, if you say you define a relation, like A not equal to B as whatever, like maybe that's just a good example, but so you define a relation on two things which unfolds to just some other expression, right? And then say I want a function that takes two related arguments and does something. So in ACTA the problem is if the relation unfolds to something, then ACTA unifier might not be able to construct these two arguments to the relation, because it's so the standard trick is to do this kind of new type thing rather than defining the relation to directly unfold. You make a new data type with a single constructor to construct this relation, and
And
this is also like a way
some variations on that are done in Lean as well.
this is
Constructing new types is a good way to block unification from seeing too many solutions and running away doing weird things.
This is also a recommended practice, because for ACTA it's actually a recommended practice to help the unifier with
I think that there are cases. I think the lean is less likely to unfold things unless it like sees that there's definitely a need to.
Okay.
Like it makes use of more of this heuristic that like if you have functions applied to the same argument and they're the same.
Mhm.
Whereas I think Agda unfolds this stuff a lot more eagerly because it wants to find all the solutions.
Right, yeah. So maybe you get away with not doing the new type thing and you can just.
But like in the error case, or like the almost error cases, it can be the case that it doesn't know, and so it tries to unfold things. And if it's a complicated definition, then it could get very bad performance, just unfolding things forever. Like if you assert a sine of x is equal to cosine of x, for instance, by REPL, then it will unfold a ton of stuff because sine x and cosine x have very similar looking definitions. It's not completely obvious whether they're identical, and so it'll make a mess while it's doing that.
In which classes will you learn about refinement types?
Refinement types aren't a thing in. I mean, okay, subtypes are a thing in lead, so that's kind of like refinement types.
But
But they're just more inductive.
they do of automatic conversion or not?
So suppose you have.
Like vector is a refinement type of okay.
Something like this.
Yes.
That works.
Okay, that's good.
That's using coercion, so you see that it's actually unfolded, or like it's inserted a coercion, and then the coercion has unfolded directly to this subtype.val function. This doesn't all like I'm not sure. Will this work? This will work. There are probably some examples where you get different behaviors depending on, like, oh yeah, that's fun. Like here, if I have id x as a nat, then it decides the identity should be over the natural numbers, and we get the x.val on the inside. Whereas if I do id x plus 1, it decides that the id x, this is the identity function on subtypes, and the val goes on the outside. And that has to do with order of elaboration and stuff. So where coercions get inserted is a little complicated. If you want to control it, you can use this arrow.
Oh.
Up arrow, which.
The up arrow is like asserting to lean that there's like a coercion that will happen here. And then there's a type class that figures out like coercions from A to B. What is it? There's a way to get coercions transitively. There's a bunch of stuff related to that.
Can you disable automatic coercions also?
I don't think you can, actually. You can disable like the way that they get displayed, or like you can change the way that they get displayed, like using arrows or using nothing or stuff like that. Although I think a lot of these coercions, maybe subtype.val is special and or haven't imported enough, but I think a lot of them go through a type class that actually does print as an arrow. So you'll see the arrow instead of this dot val. I think maybe if I do the same thing but I have method imported, it won't show dot val and it'll instead show up arrow. Yes. You can see it says up arrow.
I have another question. So the classes are usually organized like, for instance, order, and then you take a type, and then it's kind of a record like containing some. What if I want to have an order type, basically a type with an attached order? Can I?
Type with an attached order. Oh yeah, that's like So you can do. So what's it? Thanks.
Like
So-
a stacked up thing, like it would be like a group where the carrier is part of the structure and then,
Oh, I
and
see,
then-
I see.
because usually group is a type class on a,
Yes.
it's a
yes.
predicate on a type and then
So there's group, which is like this.
yeah.
But there's also is that a thing? Group cat. Or is it bundled group? I might need to import. Oh. Uh-huh. Yeah, so bundled is used. I think there are other examples of this in. I forget the name now. But there are a bunch of there's a bunch of like structures that use this bundled constructor in order to build like bundled groups and so on.
Mhm.
And a bundled group is just, the sigma type. Well, no. What is it? No. I think it isn't. It isn't a group. What are you talking? Oh, it's not a add group. Yeah. So that's an example.
Mhm.
And there's a name for this definite like bundled of various things will also have names of their own. I can't remember what they are. But those get used in particular because that will be the input to category, for instance. So that's why this is in the category theory library. Is because like there'll be the category of groups whose objects are bundled groups and whose morphisms are group homes, right? Okay. So now what I want to do is sort of open up the floor a little bit and have a discussion about like project ideas and like if people are feeling like they need a bit more guidance before they can just pick a project and so on. I feel like maybe we can look at these project ideas some more and things like that. But otherwise, I think this is sort of open mic, as it were. So, so how are people feeling in general about like? Do you want to see more of like what are the general areas that people want to investigate? Maybe that's a good way to start. So like.
Yeah.
I'll separate things into three general categories. We have sort of math formalization, like a lot of these undergraduate mathematics and so on. We have CS formalizations, like the simply type lambda calculus stuff I did last time. Or we have like tactic writing, metaprogramming, that kind of thing. Or something else. I guess you could, there are more categories one can make, but let's just start with those three. So maybe quick show of hands on just your interest, and of course non-exclusive. So would you like to do one of these mathy kind of things?
Yeah, I mean, as someone who hasn't done like a lot of math or improving, I think that would make it like this would be a good course to like actually get in the weeds with that. Rather than just
No,
doing
I mean that's
all
absolutely the case. Yeah,
programming.
if you feel good. Okay, how many people want to do sort of CS-oriented formalizations? Okay. And how many people are interested in doing this sort of metaprogramming or looking into lean internals or writing tactics?
I do have interest in that as well.
Okay. And is anyone just completely lost and has no idea about any of these projects and is?
I think like my sort of issue is like I'm so uninformed about like a lot of what would be interesting about the math stuff. It's like, okay, I just kind of choose one of these at random or whatever, or a couple of them at random from the list. But if you have any kind of like opinions about especially good ones, that would be nice.
Unfortunately, I don't have that many opinions, or at least I was not able to prepare opinions on short notice. But
No,
yeah.
yeah, this weekend.
Yeah, so take a look at these, at all these links here, and look for things that look interesting, and come with ideas, and then we can talk about them on Tuesday.
Yeah.
Okay, so is everyone feeling prepared for Tuesday? Okay. If not, or if that's all, then I mean, I can. So yeah, I think we can probably just call it a day, and then I'll see you on Tuesday.